Hey guys, it's Mrs. Conway. So what I want to do right now is I want to go over task 9 from unit 6. So we went over this in class, but I know there were some people that weren't there, and I've got online students, and this activity, I'm not sure if you would really be able to just figure it out on your own. So what we're supposed to do here is it says 6 physicists describe the amount of radioactive substance Q in grams left after T years. Show that the expressions describing the radioactive substance are all equivalent. So we're supposed to be showing that they're essentially the same thing. So first of all, I think I should probably just review the exponent rules because everything here has exponents. So just if you recall, when we multiply the same base, I'm writing that wrong for some reason. When we multiply the same base, so like x to the a power times x to the b power, we're actually going to add the exponents. So it's x to the a plus b. Now in this one, as you can see, we're probably going to be using the rule backwards, but it goes both ways. They're equal. The next rule would be if you have x to the a power raised to the b power, then you multiply a and b. So you multiply the exponents. Again, looking here, we can see we might be going backwards with that rule. If we have x to the a over x to the b, so division, then that's x to the a subtract b. So dividing, if we're subtracting the exponents, we divided them to start. And then negative exponents. If you recall, negative exponents make fractions. So like if I have x to the negative a, that is 1 over x to the positive a. So you just find the reciprocal of x. And then lastly, just a little refresher, if you have a fractional exponent, like x to the a over b, then that is going to equal the root of x. So it's going to be the b root of x to the a power. So, you know, if b is 2, it would be a square root. So anything to the 1/2 power is also just a square root. So there's our rules, little refresher in case you forgot them. Okay, so let's look at these 1, 2, 3, 4, 5, 6 functions. What they're saying is that those are actually all describing the same function. Now, one thing you could do would be to get a graphing calculator and put those all in your graphing calculator, and they would all make the same graph. Another thing we can do is manipulate them algebraically, which I think is sort of the purpose of this activity. So what I'm going to do, and this is going to feel a little weird, I'm going to look through these. I've got 300 times 0.5 to the 2t, 300 times 2 to the negative 2t, 300 times 0.0625 to the t over 2. Notice a lot of these are starting with 300. D is 300 times 0.25 to the t. And we've got 75 times 0.25 to the t minus 1. And 600 times 0.5 to the 2t plus 1. Oh, and I guess I forgot to mention, this worksheet is on Teams. I believe it's in Unit 6, Lesson 3 worksheet is what I called it. Yes, that's exactly what I called it. And there are 2 worksheets. There's Task 9 and Task 11, which I'll make a separate video for. So, if you want to go ahead and try and manipulate these to make them look all the same, you know, hit pause, give it a try, and then hit play and see if you did it right. But what I am going to do, I'm going to try and make them all look like D. And the reason I'm choosing D is because, to me, that looks the simplest. T doesn't have anything being done to it, so I think it'll be easier to make everything else look like this than it would be to go the other way. So I'm going to try and make all of these look like 300 times 0.25 to the power of t. So let's start with A. A, I have 300, so that's fine. But then I have 0.5 instead of 0.25 to the power of 2t. Well, up here, looking at my rules, when I have an exponent being multiplied, that means originally it was power to a power. So most of the time for this, I'm going to be using these rules backwards. So I'm going to go ahead and actually grab the 0.5, and I'm going to rewrite it as 0.5 squared to the t power, because that's what this would, those are the same thing. 2t is the same thing as 2 to the power of 2 to the power of t. Well, then I can do 0.5 squared. That's 0.25, which means I end up with 0.25 to the power of t. So we can see that a is actually the same as d. All right, let's try the next one. Similar idea. Now I have 300. Still, I don't have to worry about that. That's the same, but it's 2 to the power of negative 2t. So I'm going to start with 2. I'm going to raise it to the negative 2 power, and then I'm going to raise that to the t power. 2 to the negative 2 power, if you recall our negative exponent rule, is going to be 1 over 2 to the power of 2, which is 1 over 4, which is 0.25. Or, put that in a calculator. It'll give you 0.25. Cool, so we've got A and B. Those weren't too bad. All right, take a look at C. Maybe try it on your own. Again, the 300's the same, but we've got 0.625 to the t over 2. Fraction exponent. That looks like this over here, which means I should have 0.0625 with a radical. It's going to be to the t power, but radical 2. So it's a square root. So I need to find the square root of 0.0625, which might require a calculator. I kind of know what it is, but that's because I know the answer. Now, some of you are hopefully saying, well, it's probably 0.25 because that's what's been happening so far, but let's prove it. 0.0625 is 1/4, which I hope most of you recognize is the same thing as 0.25. And a little note here, when I wrote this over here, I put x to the a. It actually can also be like the exponent. It can be inside the radical, or you can do the b root of x all to the a power. It's the same thing. Doesn't matter which way you do it. So that's what we did here. I'm going to square root the 0.0625 and then put it to the t power, so I have 0.25. Because in this case, that's what I need to do. So we managed to make C look the same. D is what we're making all of them look like, so I'm not going to mess with D. It already looks the way everything else looks. E and F, now those look harder because now A isn't right. Like on E, they've got A as 75. I'm sorry, I'm saying A. When I say A, I'm referring to this value in front of the parentheses with the exponential functions. That's the initial value usually. So that's why I'm calling that A. So we need to rewrite the whole thing and think about the whole thing. We've got 75 times 0.25 to the t minus 1, which means that t minus minus, that is going to be, if I'm subtracting here, then I would have, to undo that, if I'm subtracting the exponents, then we can rewrite it as division. So the 75 just hangs out front because that's not the base of the exponent. But it's going to be 0.25 to the t on the top of the fraction. And then subtract 1, it's going to be 0.25 to the 1 on the bottom. Well, now you've got 75 times 0.25 to the t divided by 0.25. I can just divide 75 by 0.25, and that, guess what, is 300. Again, if you want to check that in a calculator because you don't believe me, feel free. But remember, dividing by 0.25, it's like thinking how many quarters would go into $75. It would take 300 quarters to make $75. Hopefully that makes sense. And then I've got 0.25 to the t power. So I managed to make E look like D. All right, F. That's going to take some work. If you want to try that one, do it. It actually uses several of the rules, but I think you could do it. So hit pause and try it out. So hopefully you've had a chance to try it out. Obviously the 600 is wrong. Or we're going to have, that's, nothing matches here. It's like, how does that even the same thing? So let's look at it. So we've got 0.5 to the 2t plus 1. Well, when we're adding the exponents, that means we multiplied to start. So I'm going to break this up into 0.5 to the 2t times 0.5 to the 1. When we're multiplying, we can rewrite stuff in different orders, right? So you've got 600. I can rewrite that as 600 times 0.5 to the 1 power is just 0.5 times 0.5 to the 2t. Okay, well, that's 300, so that's good. But then to the 2t power, oh, we've already done that one. That's like the first one. So we already know that to the 0.5 to the 2t power is actually the same thing as 0.25 to the t power. So we managed to make F look like D. So crazy but true. These are all actually the same exponential function written different ways. Which can very much happen. We even had experienced this in class. For those of you who were there, you probably saw, or you remember, we had in a situation where one person thought that a function would be best written as, I don't remember what it was, but I think it was like 93 over 2 to the x, which made a lot of sense for the way we were talking about the situation. But I was like, well, I think of it as 93 times 1/2 to the x. And they're essentially the same thing. It's just written differently. So it's good to be able to recognize when two equations are the same, so you can know, like if you're checking an answer key, if you did it right, or if you're working with someone else, did you guys actually get different answers or just see it differently? Okay, so what does this mean? Because it's all well and good to be able to rewrite these so we know they're equivalent, but what would be the purpose of writing them the way that they're written? So let's talk about D first, because that's the one that looks, I think, the most familiar probably. If we have Q, and so I'm actually going to now be responding to question 2. Which aspect of the substance does each of the formulas highlight? So let's talk about D, which is Q equals 300 times 0.25 to the t power. Now, if you've been doing the other exponential function activities, you probably remember that 300 would be our initial value. And since we're talking about radioactive substance in grams, this would be, there are 300 grams of substance to start. Actually, let's call it, because it says after t years, so after 0 years. Essentially, it's when it was first observed, right? Because keep in mind, a lot of times when we're looking at a radioactive substance, it's been decaying. But when we first observe it is when we record it as the year 0. That doesn't mean that the function actually doesn't go both directions. You know, the substance has been decaying since before we've seen it. So like say year 2021, we observe, and we're going to call that year 0, but in 2020 it was still decaying, so we can still talk about the past. It's going to come. Okay, 0.25, that means that every year it multiplies by 0.25, so that's the same thing as, like, it's a quarter, right? 1/4 every year. So I'm seeing that as divides by 4 every year. So you could say times 0.25 or divide by 4. And then the fact that this just says to the t power means it does it every year. Okay, so that's the basic one. That's what we're seeing is like we call this a parent function in math often. So let's talk about the ones that have been changed a little. So A is 300 times 0.5 to the 2t power. So here, we're still starting at 300 grams. So that's our first observed. Okay. But now it's 0.5 instead of 0.25. So we're not talking about dividing by 4, we're talking about dividing in half. So we're saying decrease, and this is, yeah, so decreases by half. And then the 2t, that's the part that can get a little confusing. Let's just think about this logically in terms of what we know about this situation. We know that this substance is dividing by 4, is decreasing every year, dividing by 4. So if it's going to decrease in half, that's going to be less than a year. So if it's less than a year, that means that this 2t is actually telling us that this is decreasing by half is going to be, well, it's going to decrease by half every half a year, right? So if it decreases by 4 every year, it would decrease by half in half a year. Hopefully that makes sense. So the 2t is actually telling us, you might think of it as this happens twice a year. It's going to decrease by half twice every year, which means that it's every 6 months. So decreases by half every 6 months, or you could think of it as 2 times per, if that helps you make sense of why it's 2 times. All right, let's look at the next one here. Now we have 300 times 2 to the negative 2t. So that one is a little bit, it's like, okay, well, the 300 we get, that's the first observed, that's like grams at the start. But doubling, we know this function is halving. This has been, or not halving, dividing by 4. It's getting smaller, it's decaying. Why would we have a 2? That's where this negative 2 comes in. So, we know as this function, which we can assume it's exponential, right? So it's going down. As we go forward in time, the function is decreasing. So if it was doubling, that must mean we're looking back in time, which again, we've already talked about this, right? This is a substance. So before we started looking at it, it was also decaying. So if you look back a year ago, there should be, well, 4 times as much, right? If we're dividing by 4 every year. So this is saying that it doubles every, since it's negative 2, that's the same thing it says here, every 6 months we look back. You could think of it as in the past. So if we look back in the past, every 6 months it would double. So, you know, you might use that if you were thinking about, you know, carbon dating something. You want to know what happened a long time ago. Okay. C is 300 times 0.0625 to the t over 2 power. So if you remember when we did this one, we ended up square rooting because of the divide 2. But let's think of this in terms of the context. Again, this means that year 0 is 300 grams. But 0.0625, if we turn that to a fraction, that's actually the same thing as 1 over 16, which means we're dividing by 16. So if you think about how long would it take for this to divide by 16, well, it divides by 4 every year. So in 2 years, it would divide by 4 twice. 4 times 4 is 16. So this is saying we divide by 4 every 2 years. Oops, I said that wrong. Not divide by 4. We know we divide by 4 every year. We're saying we divide by 16 every 2 years. So in 2 years, you would divide by 16. Or you would decrease by, because this is 6.25%, so we're decreasing by 93%, 93.75%. Okay, so D we already did. E, 75 times 0.25 to the t power. So with this one, it might be kind of helpful to look at a table of values for this function. For this function, oops, sorry, and it's t minus 1. If I put negative 1 in for x, or t, I should say, I get 1200. If I put 0 in, 0 minus 1 is negative 1, so I'm going to have 75 is 300, which makes sense because we already established this function is the same as d, which in this one, it's clear that 300 is what y is when x is 0. And then if we put 1 in this case, you'd put 1 minus 1, which is 0. So that would be gone, so it would just be 75. So if you look here, the 75 is actually the amount of radioactive material in 1 year. And so if you're the type of person that doesn't like to start at 0 because you think, well, I would start at the year 1, 1 is where we start, then you might think of this function might make sense to you because we're starting at 1. Okay, and then this part's kind of the same. It's the 0.25, that's divide by 4, which is the same as what we had before. But that's what this minus 1 is saying that we know that the 75 is not the y-intercept. So the minus 1 is saying basically we have to factor in for the fact that we started at 1 year instead of starting at 0. Okay? So let's look at F. So this is highlighting the number of grams at year 1. F is highlighting 600. So this one's a little crazier because 600 isn't on our table, but if you look, what is 600 about halfway between? Looks to me, especially if you think about how this function goes, like 2t, we already said that's like twice a year. So that would be like 6 months. If minus 1 moves us forward 1, plus 1 is going to move us back 1. So this is kind of thinking, this is where we're at 6 months ago. And now our rate is saying we have, this is still saying halving every 6 months. But the plus 1 sort of tells us that we're starting back 1 in this case, since we're going by 6 months. That's what tells us it starts 6 months ago. So there we go. There's the different ways that you can highlight different things in the same equation. And it's important to be able to convert between these because what you're going to have to do in delta math is you're going to have to be able to find your yearly rate for a exponential growth function that might be compounded different times. So what you'll want to do is you'll want to watch the task 11 video where I go over what the difference is between compounding monthly, yearly, quarterly, daily, or whatever. So why would do that first, do task 11, and then start the delta math for lesson 3. Good luck.